cross-section of our solenoid. The difference between this solenoid that I'm drawing now and the circular loop that I was drawing before is the circular loop was just one loop of wire. I mean, okay, one loop with n turns to it, but it was not a long uniform cylinder the way a solenoid is. This solenoid is going to be a cylinder of wire that continues out of the page, and rather than the important thing being just the number of turns in the wire, the important thing ends up being the density of turns, the number of turns per what?
Unit length.
Per unit length along that cylinder, exactly. So solenoid, you'll often hear about having, 500 turns per centimeter or something like that. And that is one of the things that goes into determining the B field created by that solenoid. What are some other things that go into determining the B field created by that solenoid? The amount of current that's flowing. I've got current I flowing around that solenoid. We will have it going in that clockwise direction, which means the B field inside the solenoid will be pointing which way? I've got I going in that clockwise direction. Yeah, I'm getting the current of the B field pointing into the board inside that solenoid. Where will the B field be the strongest? Near the outer wires or here, far from the outer wires?
Near.
Same magnitude everywhere. That's the interesting and surprising thing about a solenoid is the B field is uniform. It has the same strength everywhere inside that solenoid. What's the B field out here outside the solenoid? Zero, yeah. And again, I know those field lines really do wrap back around, but if you take the limit where the length of the solenoid is much larger than its radius, the B field outside the solenoid gets weaker and weaker. It approaches zero as you go toward that limiting geometry. So I've got a uniform B field inside here. How strong is that B field? What's the formula for it?
Yes.
There's N and there's the turns per unit length.
Exactly. There's the number of turns per unit length, which I can either write as script N, or I could actually put just big N over L if I wanted to do that. So number of turns per unit length, current, U naught, and that's about it. I'm going to go ahead and give this current a name, I solenoid, just because, hey, maybe in a moment I'll be asking you to find the current induced in the current through the loops of the turbine or something like that. So there is my uniform B field that I've set up by running that current through the solenoid. Now I've got to have a spinning loop that I can use to make the angle change. I'm going to take a string, hang this. Oh, this would be a perfect time to use like a triangular Christmas tree ornament kind of thing hanging from that string, or a triangular musician's triangle. But since we already did a triangle, I will say I'm going to, I'll be boring. I'll make this a rectangular loop. I'll make this a square loop, in fact. And I'll say the side of the square is S. Okay, so I've got a square loop hanging there, and either just by letting it kind of idly rotate on that string, or because this string is actually a shaft which goes to a crank handle, which a hamster is spinning up here or something like that. One way or another, we have got this square rotating around that axis, and this is me trying to do perspective. The square is not doing. Oh, hey, what if I did do this? What if I made the square rotating like this?
No change.
Yeah, that would be mean of me. That would be evil. Is set up this whole thing and then have the square rotating in a way that does not actually change the flux through it. That would be mean as the main part of the problem. It could be a perfectly serviceable part, D of the problem or something. What if I were to rotate the thing on this other axis? Yeah.
If you did have just one of those loops that didn't have the solenoid length, and you rotated that square like that, you would have a changing flux.
I would still have a changing flux. If the square is tiny at the center of the loop, I could go back here. In fact, on this one, I could just as easily have rotated that triangle instead of changing the current through my outer Helmholtz loop. On this one, if the square is kind of comparable in size to the outer circles I've done here, in a solenoid, that doesn't matter. As long as there's room for the square to fit inside the solenoid, it's got a uniform B field in
But
it.
if it wasn't a uniform B field.
Then I would have to do some kind of integral to get the flux.
Right, okay.
And in this case, it actually wouldn't have been an easy thing to integrate, because you notice the only formula we've given you for this Helmholtz loop was the B field on the axis. We have intentionally shied away from giving you the B field at off-axis points, because that's a harder superposition integral to set up in the first place. So in this case, it would probably be beyond what we could expect to do on the exam if I had given you a large loop instead of a small one. Just because finding the B field in the first place would be an ugly superposition integral in that case. Now, in this one, finding the B field in the first place is simplicity itself, because there's your formula for the B field, and it's uniform everywhere in that region.
I don't get, so that, the B field does depend on the radius.
Yes, but we intentionally made this loop so small that we could just say the B field is uniform across that little triangular loop, and it's just equal to the B field at the center of our Helmholtz coil.
No, I mean, the radius for the equation of the loop.
Oh, depends on the radius, but it doesn't depend on, I mean, it also depends on where I am in the loop. The B field at this point inside this loop was not the same as the B field at the center. The B field at the center does depend on the radius, but the B field that points off the center would be a much more complicated calculation to do. In the case of the solenoid, the B field does not depend where I am within the interior of the solenoid. The B field's uniform everywhere.
Okay.
So I've got my solenoid, I've got my uniform B field, I've got my square of side length S, and I have got somebody turning this crank up here at a rate of, well, if I want to generate power that I could, that's compatible with the power that I take off the grid, what rate do I want to spin that, that square at? 60 cycles per second. Yeah, the AC power that we get from wall outlets oscillates at 60 cycles per second. If I wanted to match that, because maybe I'm planning on feeding some device that's meant to run on 60 cycle a second power, then I could say, okay, I want this thing to be spinning at 60 cycles per second. What I might ask you is, hey, not only is the power from the wall outlets 60 cycles a second, anybody remember what the amplitude of that power, of that voltage is?
110.
Yeah, 110 volts is, I think, standard wall voltage.
Yeah.
So we could say, if I want to duplicate wall voltage perfectly for the field, for the induced voltage around this square loop, then I would have to spin that crank at 60 cycles per second, and I would have to somehow make sure the amplitude of that voltage is 110 volts. Actually, what I would need to make sure is that the RMS amplitude is 110 volts. But since we haven't really talked about RMS amplitude as a separate thing, let me leave that alone for now. It's an important thing in engineering and circuits and all that kind of thing, but we'll leave that alone for now. So we'll just say I want the amplitude of this voltage to be 110 volts. What have I got to do to make that happen? In fact, what I could ask is, maybe the biggest current I think I can send through that solenoid is 20 amps. Maybe the radius of that solenoid is 50 centimeters. How many turns per unit length do I need in order, and we'll say that the side length of my rectangular loop is 20 centimeters. How many turns per unit length do I need in the solenoid in order to duplicate wall current, in order to get a 110 volt signal that oscillates 60 times per second? That could be a problem. So if I'm doing that, we said, okay, that means I'm going to need to spin that crank 60 times per second. How am I going to actually calculate the voltage induced in that square loop?
Be a cosine of some angle changing time.
Yeah, I'm going to say my magnetic flux is the B field times the area times cosine of phi. Help me out here. Which B field am I talking about?
B field created by the solenoid.
B field created by the solenoid. So we use this formula for the B field from the solenoid. I can say I don't yet know what script n is, but that's okay. That's what I need to solve for. So I can say the B field created by the solenoid is mu naught times I times script n, my number of turns per unit length. Which area am I talking about?
The rectangle or
The rectangle, yes. So, the induced voltage around the rectangle is the flux through the rectangle. So that area is S squared, since I think I said my rectangle is actually a square. And what angle am I talking about there? What's that phi?
with respect to time.
Yeah, that's the thing that's changing as we spin this. So I could say that that will just be omega t, where omega equals what?
60.
Pi
1 over
over
60.
2 pi over 60.
Yeah, it's 60 cycles per second, except that omega is not supposed to be in cycles per second, it's supposed to be in radians per second. I could just do a unit conversion there, essentially. 2 pi radians is the same thing as 1 cycle. That's where those 2 pi's always come from in formulas using omega, is that's essentially your unit conversion from radians to cycles. So cycles cancel. I get 2 pi times 60, so omega is 120 pi radians per second. And radians are actually considered dimensionless, so just 120 pi seconds to the minus 1. Okay, so there's omega, it's known. There, I know S, it was 20 centimeters. I know script n, well no, I'm solving for script n, but I know the current, that's I solenoid, we decided it was gonna be 20 amps. So there again is my induced voltage, I just set that equal to 110 volts and I solve, right?
No, you gotta take a derivative.
Exactly, what have I forgotten again?
Not
Fair
a
enough.
This is not my induced voltage, this is my flux. The existence of flux itself does not induce a voltage. The rate of change of flux induces a voltage. So in this case, how am I going to get d flux dt?
Derivative both sides.
Here's my magnetic flux. I want induced voltage, I want d flux dt. How do I get that?
Derivative.
Yeah, just derivative of the cosine. The only thing in there that depends on time is that cosine. All the rest of this is just constant spectators. Although you could say again, if I'm saying, but by solving one problem, we've actually taught ourselves how to solve a whole bunch of problems. Any of these things, except for mu naught, any of these things could have been changing with time. I could have had that square loop breathing, inhaling and exhaling, and its area was changing with time. I could have had the current in the solenoid changing with time. I could have had the radius of the solenoid changing with time. And all of those would have given me a changing magnetic flux. Ha! Very good. Except for the radius of the solenoid, which doesn't actually matter. The radius of the solenoid, although I've given it to you, never showed up in any of my calculations. Very good. Gosh, I thought I was going to get away with that. All right. But yeah, anything that does appear in my calculations, if any of these things were changing with respect to time, that could be how we're turning this into an induction problem. In this case, the only thing that's changing with respect to time was that phi. So the induced, as always, is going to be d flux dt. Strictly speaking, I might be writing v induced as negative d flux dt, but again, the negative sign, unless I've been paying close attention to my sign conventions all along, it's probably too late at this stage in the problem to start paying attention to plus and minus signs. So I could just say, I'm going to calculate the strength of the induced voltage. If I need to know the direction at any given moment, I'll have to go back and think about Lenz's law, think about negative feedback. So how strong is that induced voltage? Most of these things are constants. Even script n, which I don't know, is still a constant because I'm not going to have it changing as the hamster spin that wheel. But the derivative of cos is what? Negative sign. As we already said, it's probably too late for me to start caring about overall plus and minus signs. So I'm just going to say sine omega t times omega. Very good. Chain rule, I'm going to have to multiply by the derivative of what's inside there. I'm going to have to multiply by omega. All right. And there, I think we've got everything. What is the amplitude of that voltage? There's my expression for the induced voltage at any particular moment. But if I said I wanted the amplitude of this thing to be 110 volts, would I
You need IMAX.
I could just set this whole thing equal to, you know, the wall, the voltage of the wall outlets, set it equal to 110 volts. But I kind of feel like I'm trying to solve for N. Do I know all the rest of this stuff? Well, of course I know mu naught, I know I solenoid, I know S squared, I know omega. Do I know T? But the T's in there. I kind of feel like I'm. What am I missing here? I'm trying to set this to be identical to wall current, which has 110 volt amplitude.
That's 60.
Isn't it just per second for T? Because you're looking at.
No, I mean, are you saying because I took d flux dt or?
I'm saying that I don't know how to describe what I'm saying, so
Sine
just
of, like,
continue.
90 degrees gets to the max.
Yes.
So
when I talk about the
like-
amplitude of a sinusoidal signal, what do I mean by amplitude? I mean the extreme values that it hits during each cycle. So I'm not trying to find a moment in time. Instead, I'd say, what are the most extreme values that the sine omega t hits during each cycle?
90 or
Plus or minus 1.
Mhm.
Yeah, I mean, the omega t has to be like 0, 90 or 270 or something. But what are the most extreme values that this whole expression hits? Plus and minus 1. So if I'm trying to say I want the maximum voltage this thing hits during a cycle to be 110 volts, then I just set sine omega t equal to 1. So I would say this is 1 at its peak. So this would tell me my number of turns that I need per unit length is going to be V wall, my 110 volts, divided by mu naught, I solenoid, S squared, omega. And it'll probably be a hell of a lot of turns because trying to take, what opportunity did I miss here? What would I really have wanted to do if I wanted to really duplicate wall current with this thing?
the phase.
I should have built this turbine differently. How? I am generating an alternating current, or generating an alternating voltage to drive an alternating current. What opportunity did I miss that would have made it a lot easier to duplicate wall current with this thing?
Go back.
I am going back and forth. I'm spinning that crank, which means that the flux is changing back and forth during each cycle.
Cycles that divide more evenly into like the value of the wall.
Well, the problem is I wanted this to be 60 cycles per second. So my omega was really kind of non-negotiable. If I wanted to duplicate wall current, that's what wall current is. But I still missed a good opportunity here. If I was building this thing in real life, what would I have done differently? You okay?
Yeah, something just flew by my ear. It's
Oh.
weird.
Count the resistance a lot.
The resistance, I mean, since right now my target is to hit a certain induced voltage, I'm not actually worried about the resistance of this wire because I haven't said I'm trying to hit a certain induced current. The wire could be made out of plastic for all I care. It's still getting that 110 volts induced voltage. Now, if I'm actually planning on hooking a load up to it, I could say a plastic wire in series with my load is not going to work very well. But for now, I could say all I'm trying to do is match the induced voltage.
You have a bigger loop.
I could have used a bigger loop, although maybe there's not room for a bigger loop inside my solenoid or something like that. I mean, there's a little bit of room. I made this smaller than that. You're on the right track. Yes. More turns of wire where?
Run solenoid.
Well, not just on the solenoid, because that's what we're already solving for.
Oh, on the
More
loop, it's
turns of
oh,
wire on that
fuck.
square loop also. And if I had, I would get this induced voltage around every one of those turns. And since all the turns are wired in series with each other, voltages in series do add. So if I did 100 turns of wire on the square loop, I would get 100 times more induced voltage. If I did 5,000 turns of wire in the square loop, now maybe the square loop is getting too heavy to spin with that crank, so that could be a problem in itself. But probably just going with one turn of wire was a missed opportunity to make this a more efficient turbine. And yes, that could be the kind of thing that I would ask on part B of the question is how would you improve this design? So yeah.
If you were actually generating power with this, you wouldn't use a solenoid because a solenoid takes power to run in and of itself, right?
This is true unless my whole thing was, no, I've got available a really powerful DC source, but I need AC power here. So, but no, in practice, you're probably right. I probably wouldn't use a solenoid because that's a powered device in itself. I would probably use a powerful permanent magnet and be spinning this thing next to the pole of that permanent magnet. The disadvantage of that for an exam problem is that permanent magnet might not have that wonderful uniform B field that a solenoid has. So.
Why didn't we solve this for N?
Because we were saying, how many turns per unit length do I need to wire into my solenoid if I'm going to duplicate wall current by spinning that rectangle? And again, what you'll find is this is going to be a freaking huge number. This is 100 volts. Mu naught is about 4 pi times 10 to the negative 7th, which comes out to 10 to the negative 6. I'm dividing by 10 to the negative 6, which means I'm multiplying by 1,000,000. So I've already got 100 million. I solenoid was 20 amps, so now I'm down to 5 million. S squared was actually smaller than 1 square meter, so now I'm up a little bit again. I'm now probably at about back to about 100 million. Omega was about 300 cycles per second. Now I'm down below 1,000,000, but I still need several 100,000 turns per meter of wire on that solenoid. Again, if I was saying, man, that's a lot of copper wire I gotta buy, you could say, if you just did 2 turns instead of 1 on that square, now you need half as many. If you did 10 turns instead of 1, you need 1/10 as many. So that's what I kind of meant by a missed opportunity. Is, man, buying a little bit of extra wire for this square loop could have saved me a lot of wire on that solenoid. Yeah.
So how would you, when you're saying that, looking at this problem setup or this equation, how would you contribute that into?
I would say that this is the induced voltage around one loop of that square. Mm-hmm. So I would introduce another variable, which is saying, how many loops do I give that square?
Okay.
I'm gonna just call that n sub squared. And now all of a sudden, I don't need such an astronomical number of loops per unit length on my solenoid because I've taken advantage of that. Yes?
Yeah, so for that last line, the V induced equals the block of constant and then sine omega t.
Yes.
The block of constant, that is essentially the amplitude.
That is the amplitude of the induced, exactly. Including the n square, if I include the n square. And the reason I'm saying that that's the amplitude, the sign's a different thing, just kind of by definition, the word amplitude means the peak that you hit during each cycle. So you say, okay, the sine hits a peak of 1, so the overall voltage hits a peak of 1 times the rest of this stuff. So the rest of that stuff is the amplitude. All right. The major thing this test will be about, of course, is electromagnetic induction. This, we've kind of hit 3 big ways we could do an induction problem. We could change the angle between the field and the area. We could change the area, which is what we were doing over here. Another way of changing the area is the things that we've always done where you take a fixed shape loop and you drag it in or out of a region of magnetic field. Because you'd say, again, the area that really matters is the area of that loop that's suffused with the magnetic field. So if I take a square loop and I drag it into a region of B field, the area is changing because the area of, the part of the loop that's actually immersed in the B field is changing. Hey, suppose the B field extends from this end of the podium to this end. In other words, maybe here I've got a big powerful permanent magnet and its north pole is facing out like this. And if I'm right in front of that pole, I'm seeing a strong B field. And if I move sideways off of that pole, I'm now seeing almost 0 B field in comparison. So I've set it up so that right here I get the cutoff from 0 B field to a really strong B field. I could also imagine there's a big solenoid and I've just cut a little slit in the side of it so that I can move the loop into the solenoid or something like that. So as I pass the edge of the desk, boom, really powerful B field coming out of the page. All across here, the B field staying the same. As I pass this end of the desk, the B field falls back to 0. And I take this notebook. By the way, if anybody still hasn't updated your records in this notebook, here's my chance to call attention to this notebook, but also here's my chance to slide it into this region of B field, and I have put a wire around the edge of it like this. Tell me, right now, what's my induced voltage in the wire around the edge of that notebook? 0. Right now, B field pointing out of the page, right now, which direction is that induced voltage oriented? Well, let's find out. Looks like we've got flux out of the page growing stronger or growing weaker?
Stronger.
Growing stronger. So my induced voltage, if it succeeds in driving current, wants to drive current in a direction that will make that flux weaker. So it wants to create flux into the page. So I want, from my point of view, I'm looking at counterclockwise current, which I believe means from your point of view, you're looking at clockwise current as I go around here. Funny how that works. So you're seeing clockwise current around this thing, and the that clockwise current's getting stronger and stronger as this thing moves farther into the B field, and now it's at its strongest.
Well, it's 0.
Okay, now it's 0. So I lied to you when I said the current would be the strongest once I was inside here. What if I said the flux was the strongest once I'm inside here?
Sure.
That is absolutely true, except that the flux itself is not usually what you care about in a deduction problem so much as the rate of change of the flux. Was I lying to you when I said the current gets stronger and stronger as I move farther into this region? Actually, I was.
Yeah.
If I'm moving this thing at constant speed, then the rate of change of the flux was actually constant as I passed that border. So the rate of change of the flux was 0. Now it's some fairly high constant, stays that constant, now it's 0 again. And the it each time was the rate of change of the flux, not the flux itself. The flux is high, but the rate of change of the flux is 0. And then I'm leaving this region, so now the current is, from your point of view, counterclockwise, yeah. Because this time, I've got flux through this loop pointing out of the page. Induction does not want to decrease that flux. Induction wants to decrease the rate of change of the flux. So if that flux is disappearing, the induced voltage actually now wants to replace that disappearing flux. So the current will be pointing in a direction that would create new flux lines out of the page toward you to replace those flux lines that are disappearing, which means that this current now wants to be flowing counterclockwise around that thing. And the current will continue to flow counterclockwise at that same value until this thing finally leaves the region, and then the induced voltage and the induced current once again drop to 0.
Will be a square wave.
What's that?
Will be a square wave.
Yes, the induced current and or the induced voltage will be a square wave, exactly. Well, if I told you, if I just wanted to graph flux as a function of time, that would be, straight line rise, then constant, then straight line drop. But if I said instead of that, I want to graph d flux dt, that would be the square wave. It would be 0, then it would be constant, then it would be 0 again, then it would be constant in the other direction, then it would be 0 again. All right, it sounds like when it comes to electromagnetic induction, I'm kind of running out of ways to fool people. I think people have this pretty damn solid. The other thing that will be the more minor but still important aspect of this would be LRC circuits. Yes?
I'm still kind of a little bit iffy on the idea of the MC Escher induced voltage kind of thing.
Yes. Okay. We were saying that there is an identity in vector calculus that I can give you that says the curl of the gradient of any scalar is always 0.
Okay.
and we've said the E field is the gradient of the voltage, well, minus the gradient of the voltage.
Mhm.
And then we try to tell you the the curl of the E field is not always zero. The curl of the E field is minus dB dt. Something's wrong in there. Well, the thing that's wrong is this. When we tell you that for any scalar field, like voltage, so for any scalar, I'll just go ahead and call it V. The curl of the gradient of V is always zero. The converse of that statement is also true. If I've got any vector field whose curl is zero, then I can write that vector field as the gradient of a scalar. So I could, a kind of a converse, and the two statements are not equivalent. A statement and its converse are kind of making separate points, but my separate point would be this. If the curl of some vector field, I'm going to call it E, but I'm not really trying to make this a statement of physics. I'm making this a statement of mathematics, but I'm just saying, hey, we're going to apply it to the electric field. If the curl of some vector field is zero, then there exists a scalar field such that your original vector field is the gradient of that scalar. So up here we were saying, hey, if you've already got the gradient of a scalar and you take the curl, you'll get zero. Here we're saying if I've got a vector field whose curl is zero, then it is the gradient of a scalar. So slightly separate statements, but they are both true. They are both provable theorems of vector calculus. So when we say, oh yeah, I know a field that I often write as the gradient of a scalar. I write the E field as the gradient of the voltage, or the gradient of negative the voltage, but close enough that negative sign is not going to kill the theorem. The whole reason why I get away with doing that is because the curl of E is zero. Is the curl of E really zero? In a static situation, yes, it is. If nothing's changing with time, then the curl of the E field is zero, and I can write the E field as the gradient of a scalar. Once I've got a changing magnetic field, the E field can no longer be written as the gradient of the voltage. That just doesn't work anymore. It turns out you still can you can still use the voltage, but the full version of this ends up being, so the full time varying way, or the full dynamic way of doing potentials, you actually have two potential functions. You've got your voltage, which is your scalar potential, and you've got a second thing that they call the vector potential, and they usually use A for that. And it turns out that both of those are necessary in order to write your E and B fields. Your B field ends up being the curl of A. And I forget if we put a negative sign in front of it or not. It's I don't use the vector potential often enough to get all the conventions straight necessarily. But the B field ends up being the curl of that vector potential. Your E field, and you'd say, hey, that's kind of cool. In the same way the E field is the gradient of your scalar potential, the B, and for this one I know we do use a minus sign, the B field is the curl of your vector potential, but it turns out that you also need to, and this might be plus, this might be minus, just because I forget, it's not that there's an ambiguity in the convention, there's just a hole in my brain for that particular plus or minus sign, but this is either plus or minus the time derivative of A. Now, if nothing's changing, the time derivative of A is zero. And we can go back to just saying the E field is the gradient of the voltage. If I've got a changing vector potential, then I need to include that, otherwise I'm getting the wrong expression for the E field. None of that are things that you need to know at this stage in your education on electrodynamics. If you go on and do a physics major, the next big E&M class you take is going to be like a junior level E&M class where the book you're likely to use is David Griffith's book on electrodynamics. And that's where they get all this stuff straight. David Griffiths was also the one, if you remember when I was saying, hey, I can blow your mind in the last 2 minutes of lecture. David Griffiths was also the time when I finally realized, holy shit, Newton's third law doesn't work the way I thought it did, because he was the one who first showed me that example of two charges headed toward each other at a right angle like that. So there's a lot of very cool things in Griffith's book that make you kind of unlearn some things that you already thought you knew. And one of the things you have to unlearn is this is not a complete statement. There's another part to it. And the only reason we get away with this is we get away with this whenever there's no time change going on.
Okay.
Just if we are not going into a physics major, but we're curious, how much prep work do you need in order to take that?
4B.
That's it?
Yes. Griffiths, in fact, will start out by teaching you the vector calculus that you need, just in case your vector calculus in 5C left any holes in your understanding. But yes, you could finish this class. There are 2 books that I suggest you pick up now that you have finished 4B. One of them is the Feynman Lectures on Physics, specifically Volume 2 of the Feynman Lectures on Physics. You now are in a good position to read that book. The second one is David Griffiths, who will kind of expand. I mean, physics education is a spiral staircase. Griffiths doesn't pick up where we left off. Griffiths goes back to the beginning and will teach you Coulomb's law all over again and start over from the beginning of electrodynamics. But this time through, you're doing it with more advanced mathematical tools. And yes, you are right now in the position you need to be in to have a great time reading Griffith's book. And Griffith's book on electrodynamics is a really good book. It's one of my favorite physics textbooks. And you know that I don't tend to give high praise to most textbooks. Griffith's is seriously good. Yeah.
So the Feynman, all the volumes of Feynman lectures can be found on the Caltech's website.
Oh, can they?
Free.
Awesome. I'm glad Caltech does that. Yeah.
They're also in the Cabrillo library.
Okay.
Yeah.
And yeah, I can loan you my copies of it. But yeah, Feynman lectures are an excellent read. Feynman, they started from a course he taught to the freshmen at Caltech. And according to Feynman, the course was a disaster. He was skipping around too much, and the students were all confused and couldn't follow what the hell he was talking about. But if you go back after you have taken a class like the 4 series, and you say, now I don't need him to present this in an organized way, I just need him to tell me cool things, at that point, the Feynman lectures become absolutely awesome. So I know teachers who try to say, let's use the Feynman lectures instead of a textbook. And I always say no. But if you say, let's have people read the Feynman lectures after they finish the class, yes, that's perfect. What?
All three volumes.
Oh, and you're on the Caltech website for that? Beautiful.
You just Google Feynman lectures Caltech, and it's the first link.
Yes, and I mean, I'm not surprised that Caltech wants to make those publicly available, just because, that's part of the legacy of Caltech is that set of books. All right. If we were to also give some LRC circuit problems, what would we want to know about those? You've got your formulas for the reactance of each of the interesting elements. Suppose I were to give you a circuit that looks something like... this. It'll give you an AC source. So it's got amplitude V naught, and it's got frequency omega.
Yes, pictures.
And try this. Got a 30 ohm resistor, and we'll say that V naught is 90 volts. a 50 microfarad capacitor. On this branch, I have got a 300 ohm resistor. And a 20 millihenry inductor. Henrys are our units, not inductors, yes. Microfarads, I've required by like the Institute of Physics dad jokes to try to probably make a pun on microscopic ferrets, because that's just the traditional pun to make at this point. So I've got 50 really tiny ferrets running around the circuit right there, or something like that. However, so here's my circuit. A couple things I could ask you about this circuit. Okay, first off, what do you think the resonant frequency of this circuit is?
Oh, 1 over the square root of LC, right?
Yeah, I mean, I know this is not a perfect series circuit like we've seen before, but it is going to turn out that even for this slightly different setup, yeah, the resonant frequency, the one where I would get the strongest current flowing in and out of this power supply, is going to still be 1 over root LC. So it would take 50 times 20 is 1,000. Micro times milli is 10 to the minus 9th. 1,000 times 10 to the minus 9th is 10 to the minus 6th. Looks like this, and square root of that is 10 to the minus 3. Looks like this comes out to 1,000 radians per second. Why does it come out to such a nice simple number? Well, because I made it that way when I made up the inductance and the capacitance there. So our resonant frequency for this circuit is 1,000 radians per second. How would I convert that to cycles per second again?
Times 2 pi.
Divided by 2 pi.
Yeah, we divide actually by 2 pi, but the conversion is again 2 pi radians equals 1 cycle. So I'd say 1,000 radians per second times 1 cycle per 2 pi radians would give me something. 2 pi is roughly 6, so this would give me something like 160 cycles per second. Okay. What if I drive this circuit at a frequency that is much, much greater than that? So if I drive this thing thousand radians per second. What will be the amplitude of current through the power supply? And you can answer this, as it turns out.
Oh.
When I say much, much greater, as great as you need it to be to get a simple answer to this. But what's the limiting case as omega goes to infinity of the current through that power supply?
The reactance.
Okay, I'll give you the reactance formulas. The reactance of that inductor is omega L. The reactance of that capacitor is 1 over omega C. But I'm not expecting you to do any calculations, or at least no calculations that you can't do in your head. How would you tell me the amplitude of the current?
We go to 0.
Ah, which one? What goes to 0? Okay, yeah. If I've got a really high frequency, the impedance of that capacitor is going to go to 0. How about the impedance of the inductor? It's going to go to infinity, which means this circuit, how could I redraw this circuit in a much simpler way? The capacitor actually becomes a wire, a short, and the inductor becomes a broken circuit.
Hmm.
So what's the amplitude of that current? 90 over 30, which is 3 amps. So yes, in that limit where I can treat this as essentially zero impedance and I can treat this as infinite impedance, then the only impedance left, the only reactance left in my circuit is this resistor. This resistor is still here, but the 300 ohms doesn't matter because it's in series with infinity, so no current runs through it anyway. What if I were to, so my answer in this case is 90 volts over 30 ohms gives me 3 amps. And the way you would kind of think physically what's going on is, yes, that 3 amps is charging and discharging these capacitor plates, but it switches direction so often that it never gets a chance to put any appreciable charge on either plate. Since it's, we're taking the limit as the frequency goes to infinity, we end up just really not charging up this capacitor at all, which is why it's acting like a short. It's letting me run current back and forth through it. When I talk about running current back and forth through a capacitor, again, it kind of seems like a weird thing to say because the charge carriers can't cross that gap, but it doesn't matter. The current can still flow. A charge carrier that lands on this plate is replaced by one that leaves this plate. Yeah.
How do you know that that could happen at the same time?
Same time as?
That the capacitor could be not charged while the inductor.
Well, over here on the inductor side, maybe there is some current running on this side. However, whatever the amplitude of the current is on this branch, the inductor, the voltage across it is, goes as di dt. So through here, the current is changing so rapidly that, if I try to put even 1 nanoamp of current over here, I might find that no, omega times that gives me such a huge voltage drop here that I can't sustain it. It's bigger than the voltage drop across this thing. In other words, this is acting like something that will not allow any current at all to flow. Because if current does try to flow through that inductor, it's changing so rapidly that it'll create a huge voltage drop across the inductor, which means I would need to apply a huge voltage drop to keep that happening. Now, I'm not saying the current really literally hits 0, unless you're taking the frequency literally to infinity, but you can say that once this impedance is much greater than 300 ohms, then I can kind of say this side of the circuit, the 300 ohm resistor doesn't even matter anymore. This guy's got a much greater impedance than that. And that's what's giving you almost 0 current on this branch. So close to 0 current that I can just approximate it as if that branch had been disconnected altogether. And just, the source is feeding current just through this branch. You could say, hey, there's Kirchhoff's rule again, just kind of saying the current coming out of the source is going to do 2 things. It'll feed current down this branch, and it'll feed current down this branch. But if this branch is essentially incapable of accepting any appreciable amount of current, then the current from the source is just the current through this branch, and the current through this branch is really just following Ohm's law. The capacitor is acting like a 0 impedance thing.
So just to clarify, when the high frequency causes the inductor to be short or breaking the circuit, then the only impedance would be just that one resistor, not the other resistor.
Right. This resistor no longer matters because it's in series with a break. This resistor does matter. And again, it's not truly a break. If I was doing series, then you could say, you know what? If either of these 2 devices, so if I'm just doing my standard series LRC circuit like this, you could say, as the frequency goes to infinity, this guy becomes such a huge impedance that the current is pretty much zeroed out all over the circuit. As the frequency goes to 0, this one becomes a huge impedance. So the only time you get appreciable current is when the frequency is somewhere in the middle. That's the whole idea of resonance. When omega equals 1 over root LC, that's when you've got, a reasonably small impedance there, a reasonably small impedance there. In fact, if you start looking at the phase relations, the direction of those phasors, those impedances actually cancel each other. And that's when, once again, you say the only impedance left is my resistor. But, so for a series circuit, kind of in either extreme limit, I'm going to shut down the current from the source, which you could say is one reason why I kind of said, all right, let me, in this case, not draw my usual series circuit, let me draw these two parallel branches so that I could still have one of the branches accepting current even when the other one was not. So yeah, the limit of high frequency, this branch is where all the current's gonna go, and you know what I'm gonna ask you next. How about the limit of very low frequency, what's gonna happen?
It's just gonna be
The other break.
Yeah, this branch shuts down. Now the capacitor is going to have a huge impedance. If you think, why would low frequency do that? Well, if this thing is changing direction once every 3 days or something like that, you pretty much say the capacitor is always at equilibrium. Maybe, tomorrow it'll want a different amount of charge on it, but for the most part, I'm not needing to run any current to charge the capacitor. The capacitor is already where it wants to be. In fact, it's not allowing current to flow because any current that flowed through would change its voltage, and it's already got the equilibrium voltage it wants for the moment. So at low frequency, the capacitor acts like a break in the circuit. It shuts down current through this branch, while at low frequencies, the inductor acts pretty much like a straight wire. Now, again, you could say a real-life physical inductor might not, because it would also have some resistance to it. So, in fact, it might be this whole branch of the circuit. This could actually just be one device, but the way I've drawn it into my circuit is I said it acts like both a resistor and a perfect inductor in series with each other. But you'd say, okay, at least my idealized inductor here, at low enough frequency, there's no voltage drop across the inductor. It's acting like a wire. So at very low frequency, what would be the amplitude of the current from that source? It would again be 90 volts, this time over 300 ohms. So it would be 0.3 volt amplitude. You can see this as possibly the makings of a ranking problem, where I could give you a bunch of circuits and ask which one gives you the greatest current at ultra high frequencies, and which one gives you the greatest current at ultra low frequencies. And maybe one of the circuits is this one, which gives you almost zero current at both of those limits or something like that. But that is kind of one good thing to take with you as you leave this class and start into Carlos's or something like that, is both inductors and capacitors, they've got kind of these approximate values that are the easy, as always in physics, the extreme cases are always the easy approximations to run. The middle-sized case is always the more challenging one. So yes, extremely high or extremely low frequencies, both inductors and capacitors start behaving like very simple devices. It's in the middle that you get some more interesting behavior from them.
So with slow frequencies, when current is flowing through the capacitor, is it just that the electron carrier is just so, they'll go across, but since there's so few of them, it doesn't even represent it?
Yeah, well, it's not that there's few. It's not like the capacitor's not charged. If this is 90 volts, if I've got really low frequency and I happen to be at the moment in the cycle when I've got my full 90 volt amplitude here, this capacitor will be strongly charged. It'll have as much charge as it needs to have that 90 volt drop across it. Only current, in the same way that we said, hey, the existence of a magnetic flux doesn't mean that you've got an induced voltage. The existence of a charge on the capacitor doesn't mean that current's running. If the charge on the capacitor plates is changing, that's when current's running. Because we've said before, this current is the same thing as dq dt for this capacitor. And since Q equals C times the voltage, this means this is C times d voltage dt across the capacitor. The capacitor's got lots of voltage on it right now, but the voltage is changing so slowly that no current is running. Gladly? Yeah.
In the second case where you have a low frequency, lower frequency than the resonant, that would be 90 over 300.
Yes, exactly. So 0.3 amps of current is going to be your maximum amplitude. And we said lower than resonant frequency. We don't just mean like lower than resonance, we way lower than resonant frequency.
Okay.
Also, Another kind of set of limiting behaviors we've talked about with capacitors and inductors is if instead of sending through an explicitly AC signal with a frequency on it, I could also just ask what happens if I make a sudden change to an existing setup. So I could give you, actually I'm gonna give you that same circuit. I'll just redraw it over here so I don't need to erase the ones we had. I'll give you that same circuit, but this time I'm gonna feed it with a DC source. There's my 30 ohm resistor. There's my 50 microfarad capacitor. Here's my 300 ohm resistor. My 20 millihenry inductor. Only this time what I'm going to say is, okay, so you start out with this switch has been open for a very long time. And by the way, if this switch has been open for a very long time, what's the charge on this capacitor? In this case, it's got to be 0, exactly. If I didn't include this branch, I might have to actually tell you the switch has been open for a very long time and the capacitor, well, it can either be fully charged, it can be fully discharged, or whatever. But if I've got this branch open, then you say if the capacitor had been charged, it would have quietly been letting current oscillate around this loop, and the resistors would have sapped out the energy. So if that switch has been open for a very long time, the capacitor is definitely discharged. It couldn't have any charge left on it. Okay, so the switch has been open for a very long time, and then I suddenly close the switch. Tell me about the current in each of those two branches at this instant, the instant just after I close the switch.
It's a maximum in the one on the middle, and it's 0 on the one on the right.
Okay, yes, the current is 0 in the one on the right for that instant. How do I know that?
Oh, because there's
It's
no.
sudden change.
I'm not allowed a sudden change in the current through an inductor. I'm not allowed a discontinuous change. If I were graphing current in the right-hand branch versus time, well, the current in the right-hand branch had been 0 until I close that switch. If I suddenly said, okay, so as soon as I close it, I bet I'll start to run some current through that resistor. And by the way, if I had to put the inductor there, if I just put a resistor, then I would say, oh yeah, resistors live in the present. They're the zen of the circuit world. It would just suddenly jump to that new value of, suppose this is a 90 volt battery, just like I used to have it as a 90 volt AC source. The only difference is it's now a DC battery. If I just had a resistor over here, then I would say, yeah, the current was 0, and now it suddenly jumps to 0.3 amps. It's allowed to do that through a resistor. An inductor is not going to allow that. It's going to say, it looks to me like dIdt was infinite for that instant. Unless you applied an infinitely strong voltage spike, that ain't going to happen. Now, can you say, well, can you supply an infinitely strong voltage spike? Kind of, because a lot of times when we say infinity in physics, we don't really mean infinity. We just mean very great compared to whatever I'm comparing it to. So it could be, actually, that on another version of the problem, I say, no, you send this really powerful voltage spike through there that essentially faster than you were able to measure causes that current to change. The inductor could let that happen if the voltage spike was strong enough. However, in this case, the voltage spike is 98 volts, it's not infinity. So I could say, that inductor is not going to allow me a sudden change in the current. What it will allow is for the current to start to build up. In fact, the rate that current is building up, well, I could say, the instant after I close the switch, look, this whole node is at 0 volts. This whole node is now at 90 volts now that I've got that switch closed. What's the voltage drop across that resistor on the right-hand branch the instant after I close the switch? What's my formula for the voltage drop across a resistor? IV. How much current's flowing through that resistor at this instant? 0, because it's in series with that inductor. So at first, I don't have any voltage drop across the resistor. This side's at 90 volts. This side's at 90 volts. But what I do have is a 90 volt drop now across that inductor. So that will let me find dIdt. I can say 90 volts equals LdIdt. And that would give me this slope. It's gonna be the battery voltage over L, because L didt is gonna be the battery voltage. Now, the only thing is, once some current, starts to flow down that branch, now there is a voltage drop across the resistor. It's not zero anymore. And if, say, that voltage drop has hit 20 volts, well, now I've only got 70 volts left to apply to the inductor. So the rate of change of the current through the inductor begins to slow down. You see what we're getting to. It's eventually going to level off. It's going to give me one of those kind of, 1 minus e to the blah, 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 blah charging curves. But for the first instant after I close the switch, instant after the switch is closed, what are some things I can very easily calculate for you? We could say the current in the right-hand branch is 0. We could say di dt in the right-hand branch is the battery over L. How about the left-hand branch? What can you tell me the instant after the switch is closed?
3 on top.
The voltage across the capacitor is what?
0.
0. Notice the inductor started out with the full 90 volts across it. The capacitor starts out with 0 volts because I need time to charge those plates before I can get a voltage across the capacitor. So if on an inductor you are not allowed an instant change in current, in a capacitor you are not allowed an instant change in voltage. You've got to spend time charging those plates before you hit that new voltage. So on the in the left-hand side, the voltage across the capacitor is 0. Instead of right and left, I'll say the current through the inductor is 0, and the rate of change of the current through the inductor is V over L. The voltage across the capacitor is 0, which means how much current is flowing down this branch. This node's at 0 volts. What's this node? What's the voltage at this node? Also 0 volts, because there's no voltage drop across the capacitor. So what is the voltage drop across the resistor? A full 90 volts. What's the current through the resistor? 3 amps. So the current through the resistor is V source, the battery, over R1. So this one R1, this one R2. And finally, what's the current through the capacitor?
0. Just opposite, the same.
It's the same as the current through the resistor because they are in series with each other. And again, if capacitors don't look at a glance like something that's allowed to carry current, it's just, yeah, they are, but it's just you have to think carefully about what it means for the current to flow through a capacitor. So the current through the capacitor is V battery over R1. It's the same as the current through the resistor because it's got to be because they're in parallel with each other. Okay, that's a fairly good collection of knowledge that you can get just from that one limiting case. And I could, again, if I've got several circuits, this could become part of a ranking problem. Yes?
But the current is equal to V battery divided by 1 in the first instant, and then it's going to drop down.
Yes. So this is just the instant after the switch is closed. Because once this current has been flowing for any appreciable amount of time, it has now deposited some charge on this capacitor plate. So now you don't have 0 volts across the capacitor. Suppose I've deposited enough charge that I now have 20 volts across the capacitor. This node is still grounded. This node would now have to be at 20 volts. And now I've only got 70 volts across the resistor, which means the current is now flowing more slowly. So again, if I was to graph the voltage across that capacitor as a function of time, we start out at 0. At first it would be increasing rapidly, but then it would increase more and more slowly, and it would give you that usual asymptotic approach there. Okay, at the other end of that asymptotic curve, I could ask you about the opposite time limit. I could ask you a very long time after the switch is closed.